So this is my third and final video that covers Chapter 3 from the Chemistry 2045 textbook. And this is a continuation of the discussion on empirical molecular formulas. So this section here is new from Chemistry 1025. So if you've been watching the prior two videos from this chapter, you'd realize that pretty much everything in there you should have already seen before. At least that is my assumption. This section here is new. It is finding the empirical formula of a hydrocarbon. Hydrocarbons are compounds which have the formula of CXHY, or it may have the formula of CXHYOZ. Now the Z is OZ is actually, it basically means it also contains oxygen as well. So a pure hydrocarbon, it's only C and H. But you also can find some compounds involving CH and O or CH and N or whatever. So these problems here are going to involve these types of molecules. So the idea here is that we're going to take my hydrocarbon. This is going to be my CXHY or CXHYOZ. That's the sample in here. We're going to put it in a furnace, and we're going to expose it to excess oxygen. And basically what's going to happen, we're going to burn this. And so this is called combustion analysis. To recall that combustion basically is the formation of CO2 and water. So it's CXHY plus O2, that's what we're adding. That's always going to make CO2 plus H2O. So we have these two scrubbers essentially, these absorbers, which can either one absorbs water and the other is going to absorb carbon dioxide. And there's any other products that could get formed, maybe carbon monoxide or anything else would also put the null escape. And so if we know the mass of the water, if we know the mass of our water absorber, we know the mass of the CO2 absorber before the experiment. Afterwards, you're going to then reweigh these. That'll tell us the masses of CO2 and the mass of water that was collected. Now, how is that going to help us find the empirical formula? Well, if we know the amount of water produced, I now can then use the mass of the water produced, convert the mass of water to moles of water, and there's a ratio for every 2 H's per every 1 molecule of water, or 2 H's per every mole of water. I then can relate that back to the original compound, because the H's from the original compound were the only H's formed in the water. So for every mole of H from original compound is used to convert that into water. So we use the 1:1 ratio to figure that out. Likewise for the CO2, carbon is related to the C's on the CXHY. So if I know the number of moles of carbon dioxide you produced, that also tells us how many moles of carbon you started with. So once I know the number of moles of C and the moles of H my original compound has, I can now find the empirical formula like normal. Now when it comes to CXHYOZ, it's a little bit more tricky because, CXHYOZ plus O2 makes CO2 plus H2O. There's oxygens in both compounds. Additionally, we use some oxygen in the process of burning. So the question now is, how can I figure out the amount of oxygen my original compound had? In order to figure that out, I need to know the mass of the original compound. And if I know the mass of C produced and the mass of H produced, by difference I can find the mass of O produced, and therefore I can now find the number of moles of O produced. Or in other words, actually a number of moles O originally had. Because some of this oxygen here we produced could also come from O2. So this will be easier to see with some examples. So this is the simplest example here, calculating the amount of find the empirical formula for the top example. So I'm going to take this bottom problem here. I'm going to move this into the slide because there's a little more room to write with. And let's paste this down here. Let's get a little more space. Alright, I'll come back to that in a bit. Let's take a look at the first example. The first example is a little bit easier. Okay, so we basically produced 1.80 grams of CO2 and we made 0.901 grams of H2O. So if I know the masses of each product, I can now figure out how that's related to the original compound. So we have 1.83 grams CO2. Let's convert this down to moles of CO2. Now carbon has an atomic weight of 12.01. Oxygen is 16. 16 times 2, that's 32, plus 12, that's 44.01. 44.01 grams per 1 mole of CO2. Okay, well, we have to find the number of moles of C. Well, for every 1 mole of CO2, we get 1 mole of carbon. So this will now tell us the number of moles of carbon we have. 1.83, divide that by 44.01 equals, obviously we check our units here to see how things cancel. Grams cancel, moles cancel. So the moles of carbon are going to be 0.04158. Moles of C. We're going to do the same thing now to find the number of moles of water. Moles of water and ultimately moles of H. Remember, we're trying to find CXHY. That's what we're trying to figure out. 0.901 grams H2O. The molecular weight of water is 18.02 grams per 1 mole of H2O. Now we have to find the number of moles of H. So this is where it's important here to know what formula we're talking about. For every 1 mole of H2O, we have 2 moles of H. Okay. So grams cancel, grams of water go away, moles of water go away. Now I just have moles of H. 0.901, divide that by 18.02 times 2, that is equal to 0.1. 0.1000 moles of H. Again, I'm keeping more sig figs than what I really need, but that's okay, because as we know from the prior problems, we're not done yet. Alright, what's the next step? We compare the moles of each and find the smallest. So which one's smaller? 0.04 is less than 0.1, so we're now going to divide by the carbon. So let's divide both of these by 0.04158. Divide this by 0.04158. So something divided by itself is 1. So we get 1C. H's, so 0.1, divide that by 0.04158, we get a value of 2.4. 2.4 H. That gives us a temporary formula of CH 2.4. Now, are we allowed to have a fraction? No, the fraction is not allowed. So I'm going to now multiply this 1 and this 2.4 by some whole number to make this 0.4 turn into a fraction, to make the fraction go away. Well, it turns out if it ends in 0.2, 0.4, 0.6, or 0.8, the number I need is 5. Multiply by 5. So I'm going to multiply this whole thing by 5. So 1 times 5 is going to be C5H, so 2.4. 2.4 times 5 is 12. C5H12 becomes my empirical formula. That is the empirical formula of this hydrocarbon. Notice we cannot simplify 5 and 12 any farther. I can't divide these by 2 or divide by 3 or divide by any other number to simplify this. It's as simple as you can possibly get. So there we go. So this is the easier of the two problems which are new for Chemistry 2045. Now let's try one a little more challenging. Alright, so this involves a little more work. I'm going to leave the font a little bit smaller so I have a little more space to work with. Make this a little taller up here. Okay, let's take a look at this one. This one's got more information. Notice I know the mass of the sample. So we have CX HYOZ plus O2 arrow CO2 plus H2O. So the mass, the original mass here is 0.8233 grams. We produced 2.445 grams of CO2 and 0.6003 grams of water. Okay, so if you look at the mass, if you look at these two compounds, add up the total masses, notice it's going to be around 3 grams, a little over 3 grams. That's much bigger than the original sample. It weighs more because we also added some extra oxygen from the oxygen gas we burned with. So, but basically I had to figure out now how much of this, of a product we made, came from the original CXHYLZ. Well, we already know from the prior example that all the carbon and CO2 is related to the CXHYLZ, and all the H is related. So it doesn't matter having to deal with this O business, the oxygen. Alright, let's do what we did last time. That's what we'll start. 2.445. So 2.445 grams of CO2. Let's figure out now how many moles of carbon we have. And we're also going to find the number of grams of carbon. I need both pieces of information. So carbon, CO2's got 44.01 grams per 1 mole of CO2. And 1 mole of CO2 is 1 mole of C. So let's do this calculation right now. Write that number down, what we get. So 2.445, divide that by 44.01. It's equal to 0.0, and all fives. 5, 5, 5, 6. We'll keep 4 sig figs. Moles of C. And let's convert that down to grams as well. Let's maybe do it below here. Let's now convert this down to grams. We do that by multiplying by the molecular weight. So it'll be times 1 mole of C is 12.01 grams of C, because I had to figure out the number of grams of O. So in order to do that, I had to figure out, well, how much of this 0.8233 grams original sample, how much of this is carbon? Alright, so I have the moles of C. Let's find the grams of C. So I didn't clear my calculator. It still says 0.05555 repeating. Multiply that by 12.01. That gives me 0.6672 grams of C. Let me put these in a couple of different boxes. Let's highlight this one in blue. That's the mole. Put the moles in blue. And let me put the mass in grams in green. This is just to keep things organized, so otherwise it ends up being a lot of black on the page. So I can find these later. Alright. And let's make a little division bar, a little line here, just to kind of highlight, separate this off. Let's repeat this process now for O. For H. Same stuff. H came from water. 0.6003 grams of H2O. Water has a molecular weight of 18.02 grams per 1 mole of water. Just like the last example, for every 1 mole of water, we have 2 moles of H. So we'll do the calculation here and mark it in blue. 0.6003, divide that by 18.02 times 2. 0.06666663 moles of H. So I'm keeping at least 4 sig figs. We'll mark that in blue. That's for moles of hydrogen. Now let's convert this to grams. In order to convert this to H in the grams, I multiply this by the atomic weight of hydrogen. Hydrogen's atomic weight of 1.01 grams per mole. So it's going to say, well, times 1.01 grams per 1 mole of H. So take your prior answer, times 1.01. That gives me 0.06729 grams of hydrogen. So let's mark that in green. Now, and another page. You can see this problem is a bit longer than the prior one, just because of the extra math we had to do. Alright, so we had, let me recopy this down, just to have this part again. Control C, Control V, and there we go. Alright, so our sample originally contained 0.8233 grams total. So CX HYOZ had original mass of 0.8233 grams. And we know that some of this came from hydrogen and some of this came from oxygen. Sorry, carbon. So some of this came from carbon, some came from hydrogen, and the remainder came from oxygen. So let's subtract off what we know. So we're going to subtract off 0.6627. So minus 0.6672. 0.6672 grams of carbon. So subtract that off. That was the carbon. This was the total. Now we're going to subtract off hydrogen. Hydrogen was 0.06729. 0.06729 grams. 0.06729. 0.06729. There we go. That's right. What's left over is going to give us the mass of the oxygen. So what do we get? So 0.8233 minus 0.6672 minus 0.06729. So that gives us 0.8881 grams of O. Alright, just like the other problems, once you hit number of grams, now we define moles. Remember, we're comparing moles, not grams here. But that was so 0.8233 grams total. Subtract off the parts. That gives us what's left over. We'll convert this now into moles of oxygen. So it's 16.00 grams per 1 mole of O. So divide 16, and it gives us 0.00 5551. 5551 moles of O. And we'll mark that in blue, because that was, we could organize our moles in blue. We'll mark this in blue. Alright, now from the prior page, so that's moles of O, or moles of C. Again, I'm just recopying from the prior page, 0.05556. 0.05556. And we check H. That was 0.06663. 6663, and O was 0.00555. I'll be right over here. Moles of O, that was 0.0055551. Alright, what number is smallest? Well, it appears that oxygen is the smallest, so we're going to divide all of these by oxygen. 0.0055551. So that gives us, let's see, something divided by itself is 1, so it's 10 0.06663 divide 0.005551. That gives us 12 H's. And we'll repeat the same thing for C. 0.0556 divide 0.005551, and that gives us 10 carbons. So, for example, the one with carbon, one with the H, that was actually 12.003. That's close enough to 12. Carbon was 10.0162. That's close enough to 10. So we have whole numbers. That's good. No fractions. Finally, we get C10, H12O. And that now becomes our empirical formula. So as you can see, these combustion problems, if oxygen is involved, that involves a fair bit more work to find ultimately the number of grams of O, which can then be converted back to moles of O, which can then be turned into find the empirical formula. So as you can see, here's a lot of extra work, a lot of extra steps. If you were to make a mistake someplace, a calculator error, or a writing, if you write down the numbers wrong or something, you could really things could go bad in a hurry. So you need to be very careful about these problems, be organized, and that's how it'll work out okay. If you have any questions, let me know.